So I hope that now you are quite comfortable with dealing of circuits which consist of R, L and C and are excited by using a sinusoidal source. It may be a voltage source or it may be current source, it doesn't matter. Okay. Then there is a concept of phasor diagram about which you must be already aware in first year in basic electrical engineering, and DS must have been aware about it in their diploma studies. We have a concept that the impedance of the inductor is J omega L. Impedance is J omega L. Impedance of capacitor is 1 upon J omega C. We draw one on this axis. If we draw one on this axis, then we draw J on this axis, and 1 upon J is actually minus J on this side of this axis. So that will very clearly able to describe how voltage and currents are related to each other in phase. Means for inductor and capacitor there is a 90-degree phase shift between voltage and current for both. In one way for inductor, in the exactly opposite way for the capacitor. How we can describe that? Say for example, if current is cos omega t, if current is cos omega t for inductor, if current is cos omega t and if inductor is of value L, then voltage across it will be VL will be, I would like to again repeat, we can find it by both ways. First, differentiate di by dt, that is di by dt is what? Di by dt is minus omega sin omega t, and into L. So minus omega L sin omega t. For just simplicity, I take it to be sine. So if it is sine, it doesn't matter. Only thing is that some directions will change. If it is sin omega t, then what is its derivative? Omega cos omega t. And L, so L will come, omega will come, and cos omega t will come. Cos, we have one unpublished equality. What is that? J sin omega t equal to cos omega t. Unpublished we have, everybody works with published equality J square equal minus 1. Everybody works with published equal J square equal minus 1. We have one more unpublished equality, that is J sin omega t is cos omega t. If you presume that, everything is solvable. So cos omega t will replace by J sin omega t. J I will take it here. That simply proves that voltage is equal to impedance into current. So this is impedance. Right? So now, if I drop in current, I do not see any Z term. In current, I do not see any Z term. When I do not see any Z term on current side, then if I say that my current is on this axis, if my current is on this axis, what will be happening for voltage? It will be on because it is Z. So it would be, if this is IL, then this is VL. So this is 90 degrees phase shift, we can say. Phasor diagram. Now for capacitor, what is the situation? For capacitor, what is the situation? For capacitor, then just to make the things simpler, we presume that if voltage across capacitor is assumed, to be sin omega t, if voltage across capacitor is assumed to be sin omega t, what would be the current? Current would be J omega C cos omega t. Current is omega C cos omega t, J omega C sin omega t. J omega sin omega t is the current. Now, if you, there is one simple identity. Just for simplicity, multiply both by J. No problem will occur. So, if multiply both by J, it becomes, or multiply both by minus J. So, what becomes for this? 1, and this becomes minus. Means if I is on this axis, then V is on this axis. Right? Okay? Then if I have got an LC series circuit, if I have got an LC series circuit, then I is common. So with respect to I, VL will be on this side, VC will be on this side. Right? VL and VC. So effectively what will be there? So now either both may be same, or VL may be more, or VC may be more. So if both are same, what is going to happen? If both are same, in that case, effective voltage would be on which axis? There will not be effective voltage, voltage will be 0. If VL is more, effective voltage would be
positive
like this. So it would be an inductor, effective inductor. If VC is more, it will be an effective
capacitor.
So up to resonating frequency, it acts as up to resonating frequency, it acts as capacitor. At resonating frequency, it acts as a no impedance. LC doesn't offer any impedance, it's 0. And after resonating frequency, it acts as inductor. Is it clear? So the frequency at which inductive reactance and capacitive reactance match is the resonating frequency. And this is a phasor diagram. VL, VC both are equal. Now we are supposed to plot F. What is F? Omega upon 2 pi. F is omega upon 2 pi. Omega is 2 pi F. So for 50 Hertz, omega is 100 pi. Then on this, so if I am having this LC series circuit, R doesn't matter. So for this, you plot ZL, ZC and Z. ZL, ZC and Z. How can you plot this? Or we can plot ZLC, means impedance of inductor and capacitor series, and then also plot mod Z. What mod Z? Mod Z would be telling us and let us say there will be some R. So we we put some R also. So impedance of inductor, impedance of capacitor, impedance of inductor and capacitor together, impedance of inductor and capacitor together, and impedance of total circuit. So you plot all four. You can put a pause. ZL, how it would be? It would be XL What about ZC?
वर्णाखाली
It would be a rectangular hyperbola in lower quadrant because it is negative. And what would be ZL plus ZC? Somewhere here both become equal. So that time it is 0. And then it approaches like this. This is ZL, this is ZC. Equal and opposite. Now when we talk about mod Z, that is, and this yellow is ZLC. Right. When we talk about mod Z now, it is R square plus ZLC square root. So at this point, mod Z is R. This is R. This height R. And then it increases on both sides. It increases on both sides. Right? So it is on this side it is R plus a capacitor. On this side is R plus an inductor. On this side inductive impedance increases, on this side capacitive impedance increases. So it is peak values Vc, Vl, because otherwise they are sinusoidal, and I, peak values of voltage across capacitor, voltage across inductor, and voltage current. All are sinusoidal. Voltage across inductor will be sinusoidal, voltage across capacitor will be sinusoidal, and this current will be also sinusoidal. So what will happen? It is quite interesting. This is the resonating frequency F0. This is the resonating frequency F0. Obviously, current will maximum at which frequency? F0. Then what will happen to voltage across inductor? As frequency increases, it will go on continuously increasing. What happens now? You look at the total impedance. Total impedance is also increasing on both sides. When frequency increases, what happens? The inductive impedance increases. So current reduces. Available voltage given is same. So something will drop here. So VL and VC, the peak voltages, will have their peaks at some points. What those points are? How can you think about this? What will happen? You can find out the peak voltage. It is a function of frequency for inductor. Means for inductor, what you will be getting? Ultimately, voltage across inductor, you will be getting something A cos omega t plus B sin omega t. Then when you get A and B, you can combine it to say something C cos omega t plus phi. You can combine it. Then this is C is the peak of inductor voltage. Similarly, you will get some other peak for the capacitor voltage. Then this itself is a function of frequency. So this you can differentiate with respect to frequency, and d by dt of this only, d by d omega of this is to be equal to 0 to get its maxima. And we find that voltage across inductor will be like this. It gets peak somewhere here. Voltage across capacitor gets some peak somewhere here. Like this. It is the frequency at which capacitor voltage. Amplitude of the VC is having maximum value. Amplitude of VL is having maximum value. I is having maximum value. And at this, both are equal. At resonance, both must be equal. I would like to again clarify. Here, amplitude is 1. V equal to cos omega t. So there would be some voltage across resistor. It is a sinusoidal function. Something cos omega t plus something, or a cos omega t plus b sin omega t. There will be some voltage across inductor. There will be some voltage across capacitor. So each of them is having some amplitude and some phase. Those would be functions of frequency. All would be functions of omega. And then, as all are functions of omega, when I is peaking, it means voltage across resistor is peaking that time. When there will be some frequency at which VC will be having maximum value. means amplitude. All being sinusoidal, instantaneous voltage would be vary from minus peak to plus peak. But amplitude means suppose 50 cos omega t is one signal and 20 cos omega t other signal. Both signals are becoming zero sometime, but maximum is amplitude is 50, which is we can say as large signal having higher value. So peak or amplitude of the voltages do have different higher values at different frequencies. So at resonance, voltage across resistance is maximum. Amplitude of voltage VR is maximum. At some frequency, amplitude of VC is maximum. At some frequency, amplitude of VL is maximum. What those are, you are supposed to find out. Right? Now it's around 12:05. We take a lunch break and assemble sharp at. I am giving 1 hour lunch break. Assemble sharp at